Hello and welcome to the second installment of It Ain't Flat. In the previous video, I gave 3 proofs that the Earth cannot be flat. In this video, I'll give 3 more simple, directly observable proofs that the Earth cannot be flat. The Moon provides multiple proofs that the Earth cannot be flat. The most obvious of these is the fact that, regardless of time of day or night, no matter its position in the sky, no matter the observer's location on Earth, the size of the Moon never changes significantly. Go ahead, look at the Moon at its highest point in the sky. A few hours later, look at it near the horizon. The Moon is the same size. The size will in reality be slightly different for various reasons that I'll go into later, but the amount only varies by a couple of percent, and this is small enough to be ignored. According to flatheads, the Moon somehow hovers above the Earth at a height of, depending on which flurf you ask, around 3,000 miles. For the purpose of the current discussion, I really don't care how it stays up. All that matters is the claim that it's always about 3,000 miles above the Earth. The exact height varies depending on the specific flathead you ask, but the exact height isn't important and 3,000 miles is a good enough approximate value. So why doesn't this work on a flat Earth? If, as the flatheads claim, the rising and setting of the Sun and Moon are the result of perspective, the Moon should become smaller as it approaches the horizon. Consider the simplest case where the Moon at its highest point in the sky is 3,000 miles directly above you. You wait 3 hours and the Moon is moved so it's 45 degrees above the horizon. At that time, it will be directly above a point 3,000 miles away. A basic application of Pythagoras' theorem will tell you that the Moon is now 4,243 miles away, or about 1.4 times its original distance. The Moon's apparent size is inversely proportional to the distance, so when it's 45 degrees above the horizon, its size should be about 70% of its original size, or 30% smaller than it was when directly overhead. Just looking at the Moon will tell you this doesn't happen. For most people, the Moon at its highest point isn't directly overhead. In this case, the numbers will be different, but the principle will be the same. Either way, if the Moon remains a constant distance above the Earth, its apparent size will become smaller when it moves from its highest point in the sky. The fact that it remains the same size means, according to the laws of perspective, it must remain a constant distance from the observer. In other words, it would need to follow a circular path around the observer. If the Moon is 3,000 miles away and is on the horizon, this could be problematic for someone 3,000 miles away. The only way for everyone to always see the Moon as a constant size in the sky is if the Moon is always about the same distance from everyone. This can only happen if the Moon is a much longer distance away than the maximum distance between observers. This causes a problem, though. If the Moon is a long distance away but is always above the cosmic frisbee Earth, it should always be visible to everyone. It would never be on the horizon. On the other hand, if it goes below the horizon, it would be invisible to everyone on Earth at the same time. In other words, for 12 hours every day, the Moon is completely invisible to everyone on Earth. This doesn't happen. On a spherical Earth, this is simple. The Moon is a long distance away, and it orbits the Earth. This is simple and completely explains every observation. Since the size of the Earth is not completely insignificant relative to the size of the Moon's orbit, the distance between the observer and the Moon will change slightly over the course of a day. This amount is at most only a couple of percent, so it can be easily ignored. Next, let's look at the horizon. Have you ever been to the ocean and looked out at the horizon? Well, if the Earth was flat, you couldn't do this. You know those flathearts who say that boats don't disappear over the horizon, that if you zoom in you can bring them back into view again? They've overlooked one very important flaw in their reasoning, I'll call it. On a flat Earth, there wouldn't be a horizon. On a flat Earth, the sea and sky would fade together into atmospheric haze. You wouldn't see a sharp, clearly delineated horizon. Why do I say this? Consider the sea and sky on a flat Earth. The sea, as the flurfs like to say, finds its own level. As for the sky, for simplicity I'll say there's cloud cover a kilometer above the sea. Additionally, I'll assume there's visibility of 100 kilometers. There's too much atmospheric haze to see beyond that distance. So, what would the horizon look like in this case? This would really depend upon your height above the water, but it would vary by a small enough amount that the actual number used can be arbitrarily chosen. In this case, I'll say 2 meters. At this height, the angle between the viewer and the furthest visible point is negligibly small, so I'll ignore it and just consider the angle between the viewer and the clouds. The maximum visible distance is 100 kilometers, and its height is 1 kilometer. Simple trigonometry shows that the angle beyond which you can't see anything is about 0.57 degrees, or about the apparent diameter of the sun. Above and below that, the sea and sky will just fade together into atmospheric haze. This is, of course, a simplified version of reality. In reality, you'd be able to see indefinitely, but your view would become blocked by more and more haze as the distance increases. Let's work out what this would look like. Imagine 1 kilometer of atmosphere blocks some amount of light x. That means the amount of light getting through is 1 minus x. In other words, the amount of light that makes it through the atmosphere is its original intensity, I0, times 1 minus x. Going through a second kilometer, the intensity will become the intensity after the first kilometer, I1, times 1 minus x. Similarly, after a third kilometer, the intensity would be I3 equals 1 minus x cubed. More generally, after n kilometers, the intensity would be I sub n equals 1 minus x to the n. Granted, this is still an overly simplified version of the problem, but it's accurate enough for my purposes. There's only one thing missing from the equation. What is x? Well, we gotta work that out. Let's use my previous example of 100 kilometers visibility, but instead of saying all the light is blocked out after 100 kilometers, I'll say that 99% of the light is blocked out. So I know that n is 100. I'm using 100 kilometers. I don't care about the actual intensity of the light, only the ratio of the intensity to the final intensity. For this reason, I can set I0 to 1. Since 99% of the light gets blocked out from the atmosphere, 1% gets through, this means that I sub 100 equals 0.01. From all of this, I can work out x. I'm not going to recite the actual details. If you want to check out my math, this is the calculation. In other words, 1.0008% of the light gets through the atmospheric haze, or about 99% of the light is blocked. So instead of showing a clear horizon, with 1 kilometer of haze, this is kind of how it would look. After 2 kilometers of haze, it would be. After 3 kilometers of haze, it would be. Finally, after 100 kilometers of haze, it would become. Notice the lack of a clear horizon. Things get far worse on a clear day. A lot of flurfs claim the sky is blue because we're looking at the waters above through the firmament. Again, there's no clear consensus about how high this alleged firmament is, but if the sun is 3,000 miles above the Earth, we can assume this firmament is at least that high. So, if we can see this firmament at 3,000 miles away, we should also be able to see 3,000 miles horizontally. This means that someone on the west coast of Ireland should be able to see the east coast of Canada. I'd like to see flurfs provide photos of this. The horizon doesn't have any of these problems on a spherical Earth. The presence of a horizon is expected because, at any non-zero height, there will be a point at which the curve of the Earth is tangential to the viewer's eye line. Since the sky is well above this, the viewer will see it at a much greater distance with much more atmospheric haze, resulting in a clear delineation between the Earth's surface and the sky. The southern hemisphere is a huge problem for flurfs for many reasons. For example, the flight I took from Sydney to Auckland a couple of years ago would have had to be supersonic to make the trip in 3 hours. That was covered in an earlier video, link in the description. This, however, is not what I plan to talk about. No, there's a bigger problem for flurfs. That problem is sunset. As I said, a couple of years ago I was on vacation in New Zealand. It was early February and sunset was around 8:30 p.m. Let's see how this would look on the Flathard's Cosmic Flapjack. Auckland is at a latitude of 36.8 degrees south. For simplicity, I'll say sunset was 8 p.m. In early February, the sun would be, according to the Magic Frisbee model, above a point approximately latitude 16 degrees south and 120 degrees west of Auckland. So, what would the distance to the sun be? This presents me with a bit of a problem, because I would need to know the radius of the Flathard Space Pizza, but no flat art has ever given a consistent number for this. I could assume the circumference of the equatorial circle, for lack of a better description, is about 25,000 miles. This would make the distance from the North Pole to the equator about 4,000 miles. This would provide a number, but I have no idea if it's correct. Instead, I'll avoid the problem entirely and just call the radius of the equatorial circle r. Since Auckland is at 36.8 degrees south, its distance from the North Pole would simply be the distance r plus 36.8 r over 90, or about 1.41 r. Similarly, the distance from the North Pole to the Sun would be about 1.18 r. At 8 p.m., the angle subtended by Auckland, the North Pole, and the Sun is 120 degrees, so the distance to the Sun is easily found using the cosine law. In other words, the distance between Auckland and the Sun is more than the diameter of the equatorial circle. Looked at another way, throughout the spring and summer, the Sun should always be visible from all points on the Northern Hemisphere. Well, I live in the Northern Hemisphere, and I never see the Sun at night. Better than that, or worse, depending on your point of view, it's greater than the radius of the Flurf's magic flapjack. This means that the Sun should be visible from the North Pole any time of day or night, any time of the year. This is quite obviously horse shit. Anyway, that's all I can be bothered with. If you liked it, click things. If you didn't, click other things. Later.